Okay, good morning. It is, of course, a big pleasure to be here and give this talk. And what I will be telling you a little bit about is the Higgs gamma-gamma measurements at the ATLAS experiment. Before I do that, do let me point out that it says ATLAS experiment here. So what I'm showing you is actually the work of many, many people, some of them even here in the audience. One thing you notice is that this says measurement, which is a little bit new. It's about 2 years old. So let me just briefly recall, even though we've done this a few times already at this conference, it was 2 years ago pretty much that both ATLAS and CMS, here are the examples from ATLAS, announced the discovery of at that time we called it Higgs-like particle. You see a mass peak here in the ZZ. In the gamma-gamma spectrum was joined a little bit later by evidence in the WW channel. And in these 2 years, we've basically gone from saying, yes, there's something we see combining multiple channels to making measurements in the individual channels. And I will focus on the measurements in gamma-gamma here a little bit. And you've seen actually a lot of this already at this conference. We're disentangling the production modes to determine the couplings to standard model particles. We're measuring the mass quite precisely. We're putting first limits on its width. We measure differential cross-sections. We learn about the spin. But we've gone beyond this also and made new searches that make use actually of the new particle, looking for flame by changing neutral currents, looking for double Higgs events, looking for other states in different mass ranges. And since you've seen all the results here, what I will do actually is go a little bit, take a step back and look at what do we actually need to make these measurements. So clearly, in the start, we need a very performant trigger that finds us the diphoton events with a good compromise between having a good acceptance for the signal and a low enough rate so we can afford to write them out and reconstruct them. We need an efficient photon reconstruction to find these events. The branching ratio for Higgs to gamma-gamma is about 2 per mil in the standard model. And we need to be able to separate converted and unconverted photons. A little bit more about this on the next slide. We need to identify these photons with good efficiency and at the same time reject the very large hadronic backgrounds. And lastly, we need to have a good energy calibration to measure the mass and a good resolution. So for the next slides to make sense, let me just very briefly remind you that in ATLAS we have a tracking system that's comprised of a silicon pixel, silicon microstrip tracker, and then a straw tube transition radiation tracker that allows us to identify electrons through transition radiation, and a calorimeter made of liquid argon and lead. It's a sampling calorimeter that is segmented longitudinally. You see 3 layers here and has a fine segmentation in this direction here so we can measure shower shapes. So we reconstruct the photons. In our tracker here, we have a significant amount of material. That means about 40% of our photons convert into E plus E minus pairs, as you see here, before they reach the calorimeter. You see this here, the probability to convert for different areas of the detectors. And we need to reconstruct these explicitly in order to have a good calibration for them and in order to identify them well. And we do this by finding the tracks of the electrons and positrons in the tracker. We use the standard inside-out tracking that ATLAS uses by default. And then we have a tracking that finds late tracks by coming back from the TRT and going into the silicon or not in case they don't extend into the silicon. This gives us the tracks that give us the electrons and positrons. And in the selection, we rely very heavily on identifying electrons using transition radiation. And what this plot shows you here is the turn-on curve for the transition radiation in data Monte Carlo in the barrel region of the detector and gives you a feeling for the quality with which we model this. But do let me point out that this is pretty good in the barrel. It's not necessarily as good in all the other regions. So having the tracks, we go and find electromagnetic clusters. You see one here in yellow. And then we use these to seed the vertexing of the tracks. Here you see, for example, a nice vertex made from 2 tracks here in one of the silicon layers. It's converting. In the case we only find one of them, we still have tracks that don't start in the middle, and we can build what we call single-track conversions. So this basically gives us the converted photons. If there's no tracks at all pointing to them, to the cluster, we have an unconverted photon. And of course, PILAP has been mentioned before quite a bit in previous talks, and we need this to be robust with PILAP. What you see here is the fraction of photons we reconstruct as converted and as non-converted photons as a function of PILAP. And you see a pretty nice stability, and 20 is kind of the mean value of PILAP we've had in the ATV run. At this point, most of the photons we have are actually hadronic background, and we need our calorimeter to now reject much of the background. We need to reject a rejection factor of about 10 to the 4, and we do this by looking at the shower shapes that these candidates have in our calorimeter. You see here our photon, that's very narrow, compares, for example, to a pi0, where you see a two-peak structure. And using shower shapes and requiring our photons to be isolated in the tracker and the calorimeter, we come to a composition of events when we select diphotons that's about 75% diphoton events. So that's the sample we work with. So this is roughly the range we look at for Higgs to gamma-gamma analyses. And then the rest is basically hadronic background. So not only do we need to come to purities of this order, we also need to understand the efficiency with which we select the photons. And this we measure in data. We have multiple methods, and we do this for isolated photons. In the lower PT range, we use radiative Z decays that goes about up to 80 GeV. And these we can select with a very high purity. And we do this by basically looking at the invariant mass of the two leptons and of the lepton-lepton photon pair, and then we find our candidates here. And we do a tag and probe measurement. That means we have a photon, we can measure with what efficiency it passes the identification criteria. Now, this isn't quite high enough in ET, so we need to find other methods. One of them we use is we actually use electrons, a tag and probe method, so we find electrons, and then we account for differences in the shower shapes that they leave in the calorimeter. Here you see in green the electrons, in black the photons for one of the shapes that's particularly different for these two, and apply transformations to make the electrons look like photons. In this way we can measure the efficiency. This still brings us up to about 100 GeV in PT, and for higher PT regions, we basically make use of a purity measurement from track isolation of the candidates. You see how the isolation looks like for photons, so for true photons, for background, and combining this with some cut reversing on the ID cuts, we can essentially measure the identification efficiency. And you see measurements of the efficiency here from the three different methods. You see that they agree well. We can go ahead and combine them. And this brings us to uncertainties that are in the percent range on the combined efficiency, as you see here. And here's the uncertainty. And starting like at 30 is where it's relevant for the gamma-gamma analysis. And this has improved quite a bit over the last 2 years. 2 years ago, on the gamma-gamma signal yield, we had an uncertainty of about 11%, which here at IUPAP, we brought it down to 1%. So this is actually quite nice. And in the coupling measurement that's public from Atlas, this is actually the second largest experimental uncertainty. And this is why this is one of the ones we actually care about bringing down. So Marumi has already said quite a bit about the energy calibration. So let me just recall a few points. We've substantially improved the simulation of our upstream material using longitudinal shower shapes. So using the showers themselves, we can essentially constrain the material. What you can see here is a measurement of how different the material is between our simulation and our data using the shower shapes in different areas of the detector. And you can see that in many regions in the new simulation, except for one which is not particularly good, we're actually okay to 10 to 20% radiation length. We can measure this to about 5% of the radiation length. So we've implemented a relative calibration of the calorimeter layers. Again, we look at shower shapes and energy depositions from muons, electrons, and photons. we've implemented a new Monte Carlo-based energy calibration that's separate for the different types of particles. And this improves the gamma-gamma invariant mass resolution by about 10% compared to what we had before, which is, of course, very nice for the gamma-gamma mass measurement. We determine the absolute energy scale from Z to EE, and it's stable with PILUP. Some cross-checks we can make is, for example, to determine the energy scale from photons themselves. And you see a nice agreement between the photon and electron energy scale. And we check if it's linear for varying energies using J psi and Z decays. The resolution itself is something that's also very important for the signal strength for the coupling measurements. It's measured from Z to EE. Here you see the smearing that we basically need to apply to our simulation to agree with the data. And we break down the uncertainties, and also this is quite a bit improved compared to the previous calibration. How much depends really on which area of the detector you look at. And this gives you a feeling, the error bars here, for the uncertainties from the Z to EE measurements, which is the largest component. So moving on and showing you the measurements and how these systematics actually impact them. This is the mass measurement you've seen before. This is the new mass value we measure in gamma-gamma decays, 126 GeV, with an uncertainty that's about 280 MeV. And comparing to the previous uncertainty of 700 MeV, this came down substantially. And the difference in the mean value you see here is actually consistent with what we expect from the new calibration. We are separating the production processes to measure the couplings to the other particles. We do this by splitting our event samples according to the topology of the decays and what they look like. So we look for associated production here with a W or a Z by selecting events with one lepton or with missing transverse momentum or from dijets here. Then next we go ahead and select events that are consistent with vector boson fusion by looking at these two jets, basically looking for some that are separated in the detector. And the rest is heavily enriched in gluon fusion. This gives you a feeling for how the different event categories that we define that I just described here, we expect them to be populated by the different production modes. These ones below here is the VH categories. These are the VBF categories here. And then the rest is gluon fusion dominated. And turning this into signal strength measurements, which essentially is the number of events we measure with a given production mode divided by the standard model. So our expectation here would be standard model equal to 1. You can see that for the different production types, we're more or less consistent with the standard model. We can measure inclusively the total signal strength. And in the coupling analysis that I showed you here, this comes out to be this number here. And what you see is it's dominated by statistical uncertainties, but systematics follow quite closely, and the theoretical is at the same level. And the largest contributions here from the systematic uncertainties is from the invariant mass resolution and the identification efficiency. The improvements I showed you haven't been folded in here. This is an older measurement, but they will be in the next update. We are also able to measure differential cross-sections. This is on the ATV data set. And let me just briefly show them to you, a few examples. Here's, for example, the transverse momentum spectrum of the diphoton system, the transverse momentum of the first jet, of the second jet, if the event, if they're there. And you see that, of course, at the moment, the statistical uncertainties are fairly large, and the systematics basically don't contribute much here yet. And within the uncertainties that we currently have, especially if we also go ahead and quantify this looking at chi-square differences and so on, it all agrees within the present uncertainties with the predictions. So just to summarize very quickly, I think we've seen a very successful transition from Higgs search to Higgs measurements over the past 2 years. We've made precise measurements of the mass, we've made measurements of the couplings, we measure first differential cross-sections. And most of these measurements are currently limited by statistical uncertainties, but this is also partially due to the effort we made to improve the calibration, the efficiency measurements, and so on. And of course, dominated by statistics means naturally this will come down as we collect more data in the next run, But still, we will also have to work quite hard to improve the systematic uncertainties further and to find the loop back to Claude's talk. You saw that also the theoretical uncertainties are close to really mattering here. Okay, thank you very much.
Thank you very much, Kirsten. Are there any questions from the audience?
So the results are really impressive, both in understanding the efficiency and energy calibration, so congratulations. So, but I'm sure there are ways to improve, especially for run 2. So what's your vision? What's the main areas where you can improve both energy calibration and efficiency understanding in Atlas Detector for run 2?
So I think actually the first challenge will be to get back to these values with run 2 when we restart, and improving comes next. If you look at what matters for the energy calibration for photons, this is specific to photons. For electrons, it looks a bit different. There's some of them that are actually stick out as being quite large. There's how well we understand, for example, the non-linearity or don't in one of the layers. And this is something we are already working on to improving for the next run. So we can, for example, look at how does the calibration depend on what the shower looks like in the calorimeter and so on. And it just takes some time to make these studies. We can do some of this already with the current data. And these will be things, I think, picking out what are the major ones and can we work on them. Some of them depend on, for example, here, how well we understand the material in the tracking detector itself. We're just installing a new layer in our pixel detector, so we need to go back and remake these measurements, of course, and try and constrain them better. For the efficiency measurements, let me go back there. It's not so clear to me that it will be that there's one single thing we can really improve. For the radiative Z, of course, once we have more statistics, this will help enormously, and it gives us really the cleanest sample. This is limited by systematic uncertainties. It basically comes from how well do we understand these transformations. So this will be fairly difficult to improve. And this one is also more limited by systematic uncertainties, which won't be easy to bring down.
Thank you.
Are there any other questions? Okay, then let's thank the speaker again.